In this lecture, we look at filtering of signals and discuss how filtering is related to convolution. In the previous lecture, we have seen how convolution can be visualized as smoothing and an averaging operation, and we also considered the example of the moving average filter that removes high frequencies in the signal by modifying the spectrum of the signal through multiplication in the frequency domain, and therefore it is related to the convolution in time domain. So in fact, the moving average filter acts as low pass filter because it zeroes out the high frequencies in the spectrum. So majority of filters are actually based on the same principle of modifying the spectral content of a signal through multiplication in frequency domain, and that can alternatively be thought of as convolution in time domain, because convolution is certainly more difficult to understand compared with multiplication. So design of most of the filters are based on this multiplication in the frequency domain. So to understand filters based on convolution, let us consider a filter, and this filter can be a hardware system or it could be implemented in a software. And let's say that this filter takes in an input signal u of t and filters out this signal and gives an output signal v of t. So the filtering operation is based on the convolution of the input signal with a function h of t. So we can say that v of t, that is the output signal, is equal to the convolution of u and h, where h is a function that is specific to the type of filter we are using, and this function is actually called the impulse response. And as we'll see shortly, this is because h of t represents how the system, which is filter in this case, responds to a unit impulse, that is a delta function. We'll discuss this through an example in this particular lecture. So the convolution in time domain, which can be written in terms of this integral can be thought of as multiplication in frequency domain, because from the convolution theorem we know that the Fourier transforms of the output signal and the input signal and that of the impulse response are related by this expression. That is, the Fourier transform of the output signal is equal to the product of the Fourier transform of the input signal and the impulse response. And this Fourier transform of the impulse response is commonly called transfer function. So in our example of the moving average filter, we've already seen in the previous lecture that our function h of t, that is in time domain, is a rectangular pulse, and the corresponding Fourier transform h of omega is the sinc function. So convolution of a signal with a rectangular pulse in time domain is equivalent to the product of the Fourier transform of the input signal with this sinc function, and that is for the moving average filter. because filters based on convolution are designed to modify the spectrum of the signal, that is u of omega, through this multiplication given by this equation. So the design of a filter essentially involves design of this transfer function, that is h of omega. So the whole process of filtering can be summarized as: you begin with an input signal u of t, then you take the Fourier transform, and then this will give us u of omega. And once we have the Fourier transform of our input signal, we'll multiply with the transfer function h of omega, and this will give us v of omega is equal to u of omega times h of omega. And once we have the spectrum that has been modified through this multiplication with the transfer function, then we can take the inverse Fourier transform to get the output signal from v of omega. Again, the idea is to modify the spectrum of the signal through multiplication with an appropriate transfer function in the frequency domain. So you can choose a transfer function which gets rid of certain range of frequencies. They might be high frequencies or low frequencies depending upon the type of filter you want. And once you have modified the spectrum, the inverse Fourier transform gives us the output signal that has been filtered. Now recall that for the moving average filter, this transfer function h of omega was a sinc function which was a real valued function in the frequency domain. So when we multiply the Fourier transform of the input signal with this real valued h of omega, that is the transfer function, in the case of moving average filter, only the amplitude of the signal changes and there is no change in the phase of the signal. So the phase of output and the input signals are the same if we multiply u of omega with a real valued transfer function h of omega. However, in general, the transfer function is complex valued. So recall that the Fourier transform is real valued if the function in time domain is real valued and an even function. So in general, h of omega can be complex valued. That means that when we multiply our Fourier transform of the input signal with this complex valued transfer function, not only do we change the magnitude of the signal, but we also change the phase of the signal. To see how filtering can affect the phase of the signal, we can write the Fourier transform in this notation. So we can write, let's say, any Fourier transform, for example u of omega, in terms of the magnitude times e to power iota phi subscript u of omega, where phi denotes the phase and this denotes the magnitude. And the phase is given by tan inverse of the imaginary part of u of omega divided by the real part of u of omega. Similarly, we can express v of omega and h of omega in this particular notation. Now, if we write this equation in terms of this notation, we get this equation, which is just an alternate form of this product of u of omega and h of omega, that is equal to v of omega. And this can be written as the product of the magnitudes of u of omega and the magnitude of the transfer function times exponential of iota of sum of the phases of u and h. So this equation shows that the magnitudes of h and u multiply and we get this equation, that is, the magnitude of the output signal in the frequency domain is equal to the product of the magnitude of the Fourier transform of u and the transfer function, that is the Fourier transform of the impulse response. Whereas the phase phi v of omega of the output signal is given by the sum of the phases of the input signal and that of the transfer function. So this shows that the magnitudes multiply and phases add up upon taking product of the Fourier transform of two functions. Therefore, if we wish to attenuate certain frequencies in the signal through multiplication in the frequency domain or convolution in the time domain without affecting the phase, we should choose a transfer function h of omega that is real valued, so that this term phi of h is 0 and the phases of the input and the output signals are the same. And we've already seen that the moving average filter, which is characterized by a transfer function of the form of a sinc function, actually satisfies this condition. So now that we know that designing filters essentially means design of the transfer function in the frequency domain, therefore we can look at design of filters. So design of filters work on the principle of zeroing out certain frequencies through multiplication in the frequency domain. So let's consider an example of an ideal low-pass filter. So an ideal low-pass filter has a transfer function given by this. So the transfer function is 0 for frequencies having magnitudes greater than a frequency omega c, and this frequency omega c is called the cutoff frequency. And if omega lies between minus omega c and omega c, then the transfer function for an ideal low-pass filter takes on a value of 1. That means the transfer function of an ideal low-pass filter looks something like this. That is, the transfer function is a rectangular function between minus omega c to omega c, and the maximum value is equal to 1. So clearly, if I take this transfer function and multiply with the Fourier transform of an input signal, then what this function will do is that any frequencies which have magnitude greater than omega c, that is in this region over here and over here will be completely zeroed out. So there is a sharp cutoff, and all frequencies having magnitude greater than omega c will be completely cut off, and therefore this is called an ideal low pass filter because we are removing the high frequencies with a sharp cutoff. So the ideal low pass filter allows all frequencies below this cutoff frequency to pass through unchanged, and it cuts off all other frequencies above the frequency omega c. And note that this ideal low pass filter is different from our moving average filter. In moving average filter, the function h of t was a rectangular pulse in time domain and its transfer function was a sinc function. In this particular case, in the frequency domain, our transfer function is a rectangular function, and we can expect that in time domain the impulse response function would be a sinc function. So h of t for this ideal low pass filter should be a sinc function. And we can verify this through a quick calculation. So using the definition of the inverse Fourier transform, we can write h of t as this integral. And because h of omega takes on a value of 1 between frequencies minus omega c to omega c, this integral will simply be equal to this. And upon performing this integration, we'll get 1 over 2 pi iota t e to power iota omega t with limits on omega going from minus omega c to omega c. And this is equal to 1 over 2 pi exponential iota omega c t minus e to power minus iota omega c t over iota t. And this can be written as, so by multiplying and dividing by omega c, so we'll get omega by pi times sine of omega c t over omega c times t. And note that this is the sinc function in time domain, not in the frequency domain. So if you have a rectangular function in time domain, the Fourier transform would be a sinc function. And if you have a rectangular function in frequency domain, then the function in time domain would be this sinc function, because sine of omega ct over omega ct can be written as the sinc function. Therefore, filtering with this ideal low pass filter characterized by a rectangular transfer function can be viewed as convolution of the input signal u of t with an impulse response function that is a sinc function. Because convolution in time domain is equivalent to multiplication in frequency domain. Another point to note is that if we have a higher value of the cutoff frequency, that means my transfer function is broad in frequency domain, then from the uncertainty principle, we know that my sinc function would be narrow in time domain. and vice versa. So if you have a narrow transfer function, then the impulse response function would be wider in time domain. Consequently, if we perform convolution of our input signal u of t with an impulse response function that is a sinc function which is narrow, then we would still retain certain high frequencies in the signal because my cutoff frequency is now higher, and therefore not all of the high frequencies are zeroed out upon multiplication in the frequency domain. Another thing to note is that when we say that this filter is a low pass filter, we mean that the frequencies with absolute values smaller than omega c pass through this filter unchanged, while all other frequencies are zeroed out. When we say that we have a low pass filter, we also need to remove the negative frequencies having an absolute value greater than omega c, and this is because a real valued signal will have both positive and negative frequencies in the spectrum, and the negative frequencies are just because of the fact that representation of a real signal in terms of complex exponentials, as we do in Fourier transform, will involve negative frequencies along with positive frequencies. Another thing to note that we've called this filter defined by this rectangular function in the frequency domain as an ideal low pass filter because in practice this sharp cutoff frequency cannot be achieved, and one has to work with a transfer function that is not sharp, but it gradually approaches to zero. So let us look at practical example of a low pass filter. So the simplest form of low pass filter that one can think of is the RC filter. So this filter is given by this circuit. So we have a resistor with resistance R and a capacitor with capacitance C. And we consider that the input signal u of t is in terms of voltage, and the output signal is measured as voltage drop across this capacitor, and that is V of t. So therefore this circuit is my filter. To understand why this simple circuit consisting of a resistor and a capacitor can act as a low pass filter, let's look at how this output signal V of t is related with an input signal U of t. So what we can show is that the output voltage, that is V of t, and that we consider as the output signal, is related to the input signal by this differential equation. So this is a first order differential equation, and this term RC has units of time, and we'll denote it with, let's say, some time constant tau c. And this is different tau than what we have in the convolution operation. We can actually solve this equation directly in time domain for an input signal u of t, and we can show that the solution involves convolution of u of t with a function h of t. But rather than solving this equation in time domain, it is easier to look at this equation in frequency domain. And this will also serve as an example of how to solve equations or how to understand systems described by differential equations in frequency domain. And that is much easier than looking at the system, which in this case is the filter in time domain. So what we do is we take the Fourier transform on the both sides of this equation. So we have the Fourier transform of the left hand side, which depends upon the output signal V, is equal to the Fourier transform of my input signal. And note that from the linearity property of the Fourier transform, the left hand side is equal to sum of two Fourier transforms for the first term and the second term. Therefore, we can write this is equal to RC is a constant and we have Fourier transform of dV by dt plus the Fourier transform of V, and that is equal to the Fourier transform of u of t. And we can write the Fourier transform of u of t as capital U of omega and the Fourier transform of V as capital V of omega. Now we want to get the Fourier transform of the time derivative of the output signal, and recall that the differentiation property of the Fourier transforms allow us to write this as iota omega times V of omega. So the Fourier transform of a derivative of a function is equal to iota omega times the Fourier transform of that function. This equation can be written as V of omega is equal to u of omega times 1 over 1 plus iota omega RC. Note that the product of resistance and the capacitance has units of time, and therefore omega times this RC value is dimensionless. So if we compare this equation with what we started with, that the Fourier transform or the spectrum of the input signal is modified by the transfer function h of omega, then we can see that this equation for the RC filter is also in that particular form where h of omega is 1 over 1 plus iota omega RC. So for this RC circuit, we have h of omega equals to this. And now we can see why h of t, that is the inverse Fourier transform of h of omega, is called the impulse response. And this is because if my input signal u of t is the Dirac delta function, that is an impulse at time t, then we would get from this equation that the response of the system is simply h of omega, because the Fourier transform of the delta function, which in this case would be u of omega, would be equal to 1, because we've already seen that the Fourier transform of the delta function is 1. So if my input signal is delta function, then the Fourier transform of the output signal, that is v of omega, is going to be h of omega, and therefore the inverse Fourier transform of h of omega is called the impulse response, that is the response of this system, which in this case is this RC filter, to this impulse input. That is why we say that filtering based on convolution involves product of the Fourier transform of the input signal with the transfer function, or alternatively in time domain it is the convolution of the input signal with the impulse response of the filter, that is h of t. So one thing to note is that for this RC filter, unlike our moving average filter or the ideal low pass filter. In this particular case, the transfer function h of omega is complex valued. So multiplication in frequency domain is going to change the phase of the signal along with the amplitude. So let us look at how the magnitude of this transfer function looks. The magnitude of h of omega is given by 1 plus omega squared rc squared, and this would look something like this. So the magnitude of the transfer function does not go exactly to 0 and there is no sharp cutoff, but as the magnitude of omega increases, it tends to 0. So clearly there is no sharp cutoff as we've seen in the ideal low pass filter. But clearly this filter acts as a low pass filter because for high frequencies the magnitude of the transfer function is small. So if we take the product of this transfer function with the Fourier transform of an input signal, let's say which looks something like this, then these high frequencies over here will get attenuated due to product of u of omega with h of omega. So the resulting signal, that is V in frequency domain, will not have these high frequencies. So it might look something like this. Therefore, we'll say that this filter defined by the RC circuit where the output voltage across the capacitor is taken as the output signal, it acts as a low pass filter. Now to look at how the impulse response function of the low pass filter based on the RC circuit looks like, recall that we've already seen that if we have a function of the form of an exponential decay for t greater than 0 and 0 otherwise, that is a function that looks something like this, that it takes on 0 value for t less than 0 and decays exponentially with time for t greater than 0, then we have seen in one of our previous lectures that its Fourier transform is given by this. And therefore, if we compare the Fourier transform of our impulse response function h of omega with this function, we can clearly see that in our case, for the RC circuit, the impulse response function is given by 1 over RC e to power minus t over RC for t greater than equal to 0 and 0 for t less than 0. So again we have the similar exponentially decaying transfer function for our RC circuit, and note that the width of this transfer function is governed by this time scale tau c, that is equal to the RC time scale that is given by the product of the resistance times the capacitance. So filtering using an RC filter can be thought of as taking my input signal u of t and convolving it with this impulse response function h of t, that is an exponentially decaying pulse. Or alternatively, we can think of it as taking the product of the Fourier transform of the input signal with this transfer function, which is the Fourier transform of the exponentially decaying pulse. And as we would expect, if my impulse response function is wider in time domain, that is, this value of RC is high, then my transfer function, which is given by this plot over here, would be narrow in frequency domain, because for a higher value of RC, the magnitude of h of omega will take on a lower value at smaller frequency. And that means if we have a narrow transfer function, it would result in removing a bigger range of frequencies. And recall that how this RC filter works is that if we think of it as convolution of the input signal with this exponentially decaying pulse, in the previous lecture, while we were discussing the demo of convolution, we saw that if we take a step function such as this and convolve it with an exponentially decaying pulse, then the output, that is V of t, would look something like this. So clearly, if we perform convolution of this step signal with sharp jump at t equals to 0 with this exponentially decaying pulse, we'll get rid of this sharp edge and we have a smoother or a gradual increase in the output signal V of t. Or alternatively, we can think of it as, because we have this step function, the high frequencies required to represent the spectrum of this step function are attenuated, because upon convolution of this step function with this exponentially decaying function, we take the product of the Fourier transform of this step function with the transfer function, and because the transfer function decays for high values of frequencies, the high frequencies are removed, and therefore we end up in a gradual increase in the signal before it levels off to the steady value. Finally, to summarize, in this lecture we've seen that filtering can be thought of as convolution of the input signal with the impulse response function of the filter. Alternatively, this means that filtering is essentially multiplication in frequency domain, because from the convolution theorem we know that convolution in time domain is equivalent to multiplication in frequency domain. And we've looked at the example of an ideal low-pass filter where the transfer function cuts off the high frequencies having magnitude greater than the cutoff frequency. And we've also looked at a practical example of a low-pass filter, that is an RC filter, where such sharp cutoff is not possible, and instead we have a gradually decreasing transfer function with frequency. So the filters that we have discussed in this lecture are low-pass filters, but similarly you can design filters which allow high frequencies to pass through while they remove low frequencies. Such filters are called high-pass filters. Or you can keep frequencies in a certain band to be unchanged while removing all other frequencies, and such filters are called band-pass filters. So these different type of filters can be designed simply by using the transfer function h of omega, so that the frequencies that are unwanted are zeroed out by multiplication in the frequency domain. And some of these high pass and band pass filters we look at in the next lecture.